All right, guys. Happy Friday. Thought I'd do a little something different today. I know this was the worksheet that we kind of worked through last class, but I have had some requests over the last few months about trying to make some videos so students can kind of go back and look at things again and kind of review on their own. So I think last period today, it being Friday, you guys being mostly seniors, this can kind of be I guess fun day Friday. So in lieu of us meeting together, I will just have you guys watch a video when you can at some point today. All right. So here I go. Right, I'm going to go through this. A lot of this we did the other day, but I'll just kind of hit on it again. Our quiz won't be Monday; it will be Tuesday. All right. So Monday you can be prepared with questions. Tuesday we'll take the quiz. So I'll use the calculator here and I'll go back and forth. All right, so suppose that the blood cholesterol level of all men between these ages is normal. Okay, so the fact that it's normal is important for us. The problem is telling us that it's normal. We're given a mean, we're given a standard deviation. All right, it says, in a random sample, describe the distribution. Comment on center, shape, and spread. So the center is real simple. All right, it's just going to be whatever the mean is. Whatever we were told. So it's 188 milligrams per deciliter. All right, the spread, we have to do a little work. It's going to be the standard deviation that's given, which is 41, divided by the square root of our sample size. So the square root of 100 is 10. 41 divided by 10 would be 4.1, again, milligrams per deciliter. All right, that formula I'll give to you. You don't have to memorize it. As far as the shape goes, there's no work that needs to be done here other than we know that it is a normal distribution. Why? Because we are told in the problem. All right, later on I'll tell you about, well, what happens if we're not told? All right. In part B, find the probability. So when it says probability and you're dealing with a normal distribution, we are going to use, well, no sense of me writing it. I wrote it right here, menu 552, which is norm CDF. It's going to ask me my boundaries, and it's going to ask for a mean and standard deviation. All right, so they're talking about the sample mean, referring to the last problem. So we're going to use the data that the stats that we just used here. Our interval, lower bound, upper bound, mean, standard deviation. So menu, 552. 185 to 191, 188, and 4.1. 0.3, 0.537, right, 0.537. That's your answer. You can make it a percentage if you'd like. The next question says, all right, well, now we're actually going to sample 1,000 men. What's the likelihood, another word for probability, that that sample mean is between the same interval? All right, well, with more men sampled, there's going to be less variation. Less variation means I should get a smaller standard deviation, which is going to change my probability. So the first thing I need to do is say, all right, well, 41 divided by the square root of 1,000, right? I got to figure out my new standard deviation. .297, we'll say 1.297. Now, depending on how you round it, you might get slightly different answers, and that's okay. It'll be like insignificant differences. All right, great. We're going to use that. But when we go to norm CDF again here, the only thing that changes is that value. We're still dealing with the same interval. Remember, your mean stays the same because regardless of your sample size, you would expect the average to be 188. Now again, with this being smaller, with the mean being inside of this interval, we think that this probability should be a lot higher. All right, you'll see why. So 5, 5, 2, 185, 191, and 1.297. All right, so about 98%, 0.979. It says, what accounts for the different answers in part B and C? So what makes up for such a significant difference in probability? Well, it's the increase in sample size. All right, so bigger sample. And with the bigger sample, we've said it before, that'll say less variation. All right, number 2. Again, we're told here that it's normal. All right, that helps out a lot. What is the probability that A, randomly selected box of cereal? Just 1. Okay, so that means just norm CDF right away. We don't have to change anything here. Contains less than. So 0, 9.65. The mean was 9.7. The standard deviation is 0.03. So 0, 9.6, 9.7, 0.03. You know what? Was it 0.65? Yeah, it was. All right, ignore that answer. I got to change up something. Went too quick. So 5, 5, 2, 0, 9.65. Sorry about that. 9.7, 0.03. All right, we get the answer of 0.048. So 0.048. And that makes sense, right? Because think about this. If this is normal, the mean is 9.7. Let's just say here's 9.65, right? What's the chances it's less than that? Well, not so much, right? Because it's not that varied. So that makes sense. And now we're going to say, all right, well, let's actually take a sample of size 5. And if we took the sample of 5 boxes of cereal and we found their average weight, what are the chances that it would be less than 9.6? All right. And it's going to be a lot less. I mean, a lot less, right? Because the average is 9.7. If we took we could have one box that might just coincidentally be less than 9.65 ounces. But the chances of getting 5 boxes where their average weight is that low, it's probably not going to be likely. So because the sample size changes, we have to do a little work. We have to say, all right, 5, nope, not 5. Our standard deviation was 0.03. Divided by the square root of your sample, which was 5. So 0.03 divided by the square root of 5. 0.013. Now I can figure out probability by going to norm CDF. Remember, the only thing that changes here, I have a new standard deviation. Four zeros and a 6. So look, basically a 0% chance of getting this. 0.00006. All right. like we said, that would have been very difficult to happen. We knew the likelihood there was going to be extremely low. All right, and finally, and this is kind of what we didn't get to the other day, we said, even though it's not needed here, what does the central limit theorem tell us? Well, let's kind of think about, well, we'll look at both problems. First off, the central limit theorem tells us this. I'm going to abbreviate as CLT. It says if the sample is at least 30, all right, if it's big enough, the distribution is approximately normal. Now, some of you might be saying, well, isn't that large counts? Well, large counts did the same thing. It told us it was approximately normal. However, large counts is for proportions. That was last chapter or last section. This whole section we're dealing with means. So it has a different name. It's not called large counts here. It's called central limit theorem. So you don't have to go multiplying n times p or anything because there is no p. All right? This is a little less work. All you have to say is, well, is the sample size big enough? If it is, great. It's approximately normal. Well, the sample size here was only 5. Yeah, and it didn't matter because we were told the distribution was normal to begin with. All right? In number 1, if we weren't told this, okay, we still could have done B and C because our sample size was considered large enough. 100 and 1,000 are obviously bigger than 30. So we would have been able to do norm CDF for this problem because of the central limit theorem. For this problem, if this was left out, we wouldn't be able to say it's approximately normal because the sample size is only 5. All right. So, guys, I hope that helps. I want you to enjoy your Friday, enjoy your weekend. Come prepared on Monday with any questions you might have. Quiz on Tuesday. All right. Let's see if I can get out of here.